Well, in this class we'll be discussing on some simple problem which can be solved for liquid extraction. Assume we are talking about a system containing water having acetic acid of 7 mg per liter is to be extracted with pure benzene and equilibrium constant is 180 and the volume ratio of water to solvent is 80. So we want to find out here what is the equilibrium concentration in the organic phase, extraction factor and fraction recovery. So before we are going to solve this case, we are assuming the volume of benzene is 1 liter, water phase volume is 80 liter because we already know the ratio. So in this case, we know the total acetic acid in water phase before we are doing any extraction is 7 milligram per liter into 80 liter, that is 560 milligram. And once the extraction is over, they have reached in equilibrium. We don't know the concentration, we are assuming better. So I'm assuming the final aqueous phase concentration, that is 8 liter phase concentration, is Y milligram per liter. So in the organic layer the concentration will be 180 Y because we know the equilibrium constant is 180. So essentially the total amount of acetic acid in both the phases will be 80 Y plus 1 into 180 Y because 80 Y is for aqueous phase and 180 Y is for organic phase. So essentially it is 260 Y. So total amount is 260 Y after extraction, and before extraction it is 560. That means 260 Y equal to 560. Y is around 2 milligram per liter. Extraction efficiency, that is K into L by H. We already know K values here is 180. L by H ratio is 1 by 80, so it is becoming 2.25. And P is E by 1 plus E, that is 2.25 by 3.25. That is the fraction of compound extracted, that is 69% of your total acetic acid has been extracted into organic phase. Now we'll be discussing with a new topic, discussing on repeated extraction. That means instead of using the volume of extractant, we can use the same volume in multiple times in portions. So we want to see that whether there is any benefit or not. Essentially we'll do it in multiple portions and we'll see this example particularly. So this case you are considering 80 liter of water containing acetic acid, like the last example, which is to be extracted with 2 liter of pure benzene and equilibrium concentration constant is 180. If we are doing it in two different way, one is entire 2 liter benzene one time, or we are using 2 liter benzene in portion 1 liter, we are extracting the remaining aqueous phase, we are extracting once again with fresh 1 liter. So repeated extraction. Let's see how the scenario changes. Case 1 we are doing. So 8 liter 7 milligram per liter, we are using here 2 liter of our organic phase, we are extracting. We assume that after extraction the aqueous phase concentration is Y and organic phase concentration is X. So essentially you can put the mass balance over here because you know before extraction the total amount is 80 liter and 7 milligram per liter, so 80 into 7. After extraction it is 80 liter into Y and 2 liter of organic phase concentration X. So essentially we can have 80 into 7 equal to 80Y plus 2X as a mass balance. And concentration ratio at equilibrium, that is X and Y ratio is 180, so X equal to 180Y. You can solve it essentially and you will have X equal to 229 milligram per liter, that is the organic phase concentration. So how much we actually recovering? We are recovering 2 liter of 229 milligram per liter, that is 458 milligram. That is the total amount of acetic acid recovery if we are using the whole 2 liter acetic acid in a single extraction. We're doing the repeated extraction here, the same scenario, but 1 liter and 1 liter. We'll be doing it in two phases. So for case 2, the first time we are doing with 1 liter. So 80 liter 7 milligram per liter is the aqueous phase. I am taking only 1 liter of organic phase. We are extracting. After equilibrium concentration we are assuming as x1 and y1. We'll be using the mass balance equation, that is 80 into 7 equal to 80 into y1, 1 liter into x1, and x1 y1 ratio is 180. So these two equations we can solve. X1 is 387.7 milligram per liter. So how much is recovered in the first 1 liter is 388 into 1, that is 388 milligram. Now the residual water phase, whatever is still remaining, will be extracting with new 1 liter of solvent. So as we know already y1, you can see that we are having 80 liter and concentration of the compound is 2.15 milligram per liter. We are extracting with fresh organic solvent. Again there will be an equilibrium and we don't know the concentration we are assuming is x2 and y2. We will again apply the same mass balance in this window, that is 80 into 2.15 is the before extraction, the total amount of acetic acid. After extraction it is 80 into y2 plus x2. So and the relationship is still valid, that is x2 and y2 ratio is 180. We can solve it. We are getting x equal to 119 milligram per liter in the organic layer. So total recovery in benzene layer, 1 liter benzene layer is 119. So overall recovery in the two step is essentially 388 plus 119, 507 milligram, which is of course higher than the single time 2 liter extraction process. Now we'll be discussing about some idealized countercurrent stage extraction process. That means instead of using one stage or one step process, we can repeatedly do the same thing. So there is a continuous flow of the heavy liquid phase and the light phase. So essentially there are multiple stages through which they come in close contact, and they make equilibrium and moves on. And if I am going to discuss this phenomena from a opposite directionality, so that means from left to right or right to left, but for both the liquid phases, then it is known as countercurrent. Now let's see how is it going to happen and how equilibrium from one end to one end works there. But before that, we will also show you one example case, the stage nomenclature. As you can see, we are talking about multiple stage. Assume one of the stage is stage number 23. So this stage will have two input. One is of course heavy phase, another is the lighter phase, which are coming from opposite direction. That's why it is known as countercurrent. So green arrow and red one is showing the lighter phase and heavy phase respectively, and we are writing the L is the volume, H is the heavy phase volume, and you can see the concentration in the lighter phase and heavy phase are also given in terms of X22 and Y22. So here the suffix whatever we are putting here, I will say not suffix, I will say the subscript rather for X and Y 22 or 24, they have actually some naming convention here. So any stream coming out of a stage, it will have that particular number. So here when you see X22, that means it is coming out from 22 number of stage, and when you're saying Y24, that is originating from 24th stage. So that's why it is Y24. Now we are giving some mixing time. They will be equilibrate and they will come out as H and L again, and their number will be Y23 because both of them are coming out of 23rd phase. They are also in equilibrium. If you are having multiple stages, the picture will be just bigger scenario. We will have multiple stages. You can see, particularly you can see the stage are numbered from right to left side increasing. The latter phase is x0 equal to 0. That means initially there is no drag in the latter phase over here, and finally it is coming out at the extreme left arrow, that is you can see LXN. And heavy phase we can see is entering from the left extreme size from H yn plus 1, and it is coming out in the right hand side as y1. Now we'll take one example around the first stage. You can see I will just highlight it. So essentially, the input to the stage is x0 equal to 0, the fresh solvent, and y2, that is the heavy phase, that is the input, and x1 and y1 concentration of light and heavy phase, that is the output. So total input and total output, if we make a mass balance around this stage, we will find hy2 plus L into 0 equal to hy1 and Lx1. You must know that x1 and y1 is actually the stream which is coming out of the stage. That means they are in equilibrium. So we can say instead of x1 ky1. So just rearrange the equation, we can also write y2 equal to 1 plus lk by h into y1. So it simplifies to y2 equal to 1 plus e into y1. So concentration of the heavy phase out of the stage 2 is related to stage 1. So this process we can also do maybe for a bigger scenario. Multiple stages are there. Let's see what happens if I'm going to take or consider on stage 2. So now we're focusing on stage 2. Stage 2, you can also see there are two input to the stage 2, that is hy3 lx1, and coming out is lx2 hy2. So mass balance is again the same way. Now we'll have some little rearrangement before we are going to discuss further. You can see here, you already know hy3 lx1 hy2 lx2. Just now we'll replace x2 in the other hand side, so we'll rearrange hy3 equal to hy2 lx2 minus lx1, and we can simply write, instead of x1 and x2, we can write in terms of y1 and y2, that is ky1 ky2. So there is no x term here, which can further be simplified in terms to get y3, that is y3 equal to y2 plus lk by h y2 minus lk by h y1. lk by h you already know, that is e. So essentially you can say y3 equal to y2 plus ey2 minus ey1, and rearranging you can say y3 equal to 1 plus e y2 minus ey1. y2 we already know that it is 1 plus e into y1. Substitute it out, and simplification will get y3 equal to 1 plus e plus e square multiplied y1. So third stage output and first stage output is connected. So if we do the same way for third stage, and we'll go for fourth stage at any number of stages, we'll have y4 will be like this change. You see the trend, 1 plus e square. So it will be 1 plus e plus e square plus e2 into y1. For nth stage, we can write ym plus 1, that is the input to the nth stage, equal to 1 plus e plus e square plus continuing e power n into y1, and which can be rewritten as e power n minus 1 by e minus 1 into y1. So essentially the relation talks about the heavy phase input concentration, that is heavy liquid feed concentration, and heavy liquid exit concentration. So both the side is actually talking about heavy phase concentration. We'll have some mathematical problem preferably on this, which will be more easy for understanding. You can see here you want to find out the fraction extracted part also before you are solving. That is, we already know fraction extracted means the amount which is in latter phase coming out total, and how much was there originally in heavy phase. So essentially 1 minus y1 by yn plus 1, and y1 we already know e minus 1, yn plus 1 is equal to n plus 1 minus 1. Rearrangement is little bit, that's all. Now we'll be solving one numerical problem given here. We are having a fermentation broth, concentration is 260 mg per liter, which is to be extracted with butyl acetate. Equilibrium concentration is given 60. You want to plan to have heavy liquid concentration, that is heavy phase concentration is 450 liter per hour, and latter phase 15 liter per hour. We want to have 95% recovery of the antibiotic. How many stages are required here? So first step is you can calculate what is value of E, that is K into L by H. K is 60, L is 15, and heavy phase flow rate is 450 liter per hour. So if you simply do it, we can find out value of E is 2, and we know we want to have 95% recovery. That means if we go to the original equation, left hand side you see 100% heavy phase, and 5% will come out through heavy phase because 95% is being extracted. So we can see yn plus 1 is 100, y1 is 5, and number of stages, for example, we don't know, we are assuming n. So the equation following the earlier one we can use like this, and we will have n equal to 3.39, that equal to 4. That means we are going to use 4 stages for 95% recovery of the antibiotic process. Do you have any questions on that? You can put me a SMS, or you can raise questions in Google Classroom. Thank you.